Alright, we're going to start the lesson for solving trig equations for day 2. So I'm just making sure it's big enough for us to see, and we will begin. Okay, so it's a continuation of day 1 to the extent that we are solving trig equations. So if you think about day 1, we were given linear equations and quadratic equations to solve trigonometric equations, right? So sort of similar, we're still going to be solving a trig equation. Remember, when we're talking about solving a trig equation, we're solving for that theta. The final step is you're looking at the unit circle and figuring out at what angle will that statement be true. So we did it for linear and quadratic for day 1, and day 2, let's look at what is different here. So sometimes you will be given an equation. So if you look at your notes, so we're basically at page 16. So if you look at your notes, you will see, for example, problem number 3. It's a little kind of not very clear, so I'll try to write it on a different piece of paper. But if you look at problem number 3, you'll see that it has a combination of sine square and cosine. It is a quadratic because this is square, and I can write it in the standard form. That's what we learned under quadratic to solve. But I have a combination of different kind of different trig terms. So there's sine square and cosine. If I treat this as an x square, this becomes an y. So how do you factor when there are two different kinds of trig terms on the same equation? Same thing for 1 and 2, but we'll start with 3, we'll go to 4, and so on and so forth. And we'll do 2 also, actually. We'll start with 2 maybe. Again, in 2 you see that there's a tangent and cotangent on the same equation. So what do we do? So this is where, if you think about it a little bit, sine square can be written as a cosine square. How? Why? Because of Pythagorean ID. Pythagorean ID says 1 minus sine square equals to cosine square, and that's exactly what I'm going to do. In this case, if I want to convert them to being the same, remember, tangent theta equals to 1 over cotangent theta. So I can replace one of them with the other, and therefore I'll have the equation with the same, and therefore I can use my it'll become easier for me to solve it. Okay, so which basically means, what I'm saying is that sometimes we have to use the different trig identities, mostly reciprocal ID, quotient ID, Pythagorean ID, and sometimes double angle identity, to solve for trig equations. So, and that's what we're going to be talking about. So some trig equations involve using trig identities to get the trig functions to be consistent. Let's go ahead and review our trig identities. We'll do reciprocal ID. So reciprocal ID is basically sine theta equals 1 over cosecant theta. Hopefully it's all coming back as I'm writing down. Cosine theta is what? 1 over secant theta. And then tangent theta equals 1 over cotangent theta, and you can basically write the reciprocal also. For example, if it's cotangent, you can write 1 over tangent, and so on and so forth. Then we'll write the quotient ID. Quotient ID is, the word quotient means you're dividing, so tan theta is sine theta by cosine theta, and cotangent theta is cosine theta by sine theta. And then we will write, then we'll do Pythagorean ID. So Pythagorean ID, there are 3 forms of Pythagorean ID. The parent one that I call, the first one that you start off with, is sine square theta plus cosine square theta equals to 1. This is what we start with. X square plus y square equals to c square. This is r square, a radius is 1, so an x and y are sine and cosine. And then 2 different forms, where you divide everything by sine, so sine by sine is 1, cosine by sine is cotangent square theta, 1 by sine square is cosecant square theta. And the last one is divide everything by cosine square, so tan square plus 1 tan square theta plus 1 equals secant square, because 1 over, sorry, I'm not writing the theta, there's no space, but we should be, here we go, sorry, here we go. So these are the 3 forms. You can also look at your formula sheet, and you find all 3 forms. I'm just writing it down for us to refer. And then we have sine double angle. Sometimes you'll use this also. So sine double angle means sine 2 theta equals 2 sine theta cosine theta, and then you have cosine double angle. And as we keep looking at different trig equations to solve, you'll see where all of these will be put to use. So this, we're talking about cosine 2 theta. Cosine 2 theta can be, there are three forms of it. I'm going to write two forms of it. 2 cosine square theta minus 1. There are three forms, but I'm going ahead and writing only the two forms, and you'll see why. These are the two forms that you will mostly use. You won't use where there's both sine square and cosine square existing. But anyway, again, you can look at the formula sheet to look. And let's go ahead and write the third one too. There's no harm in that. So these are the three forms of cosine 2 theta, double angle. And sine 2 theta is just one form, 2 sine theta cosine theta. All right. So we have listed all the IDs that we know that we will use, and we will see how we can be put to use. But right now, let's go ahead and solve the different trig equations. It says solve each equation in this interval. That means within one unit circle. Okay. So I will start doing the work on a separate piece of paper, just because I think there's a little bit more clarity. My paper has a lot of ink marks. So I'm going to start with number 2. So number 2 is tan theta equals cotangent theta. So how do you solve? You're trying to solve for theta. How do you solve this when you have both tangent theta and cotangent theta? So basically, I do know that I can use my reciprocal ID. One of them can be replaced by that. So tan theta, I'm going to keep it as tan theta. And instead of cotangent theta can be written as 1 over tan theta using reciprocal ID. You don't have to write the reason because you're not doing any proofs, but I'm just writing it so that you understand why I did what I did. Now it's easier to prove because everything is tan theta. So what is the first step you do when we try to prove? Remember we said isolate the term that contains the theta. So here both tan theta is, there's theta on both the tans. So I will try to multiply. So I want to basically get rid of the tan theta in my denominator. So, or you can also cross multiply. So tan theta times 1 is, you're multiplying 2 tan theta by itself. So it's tan square theta. 1 times 1 is 1. And then what do you do? Remember, keep telling yourself that your goal is to get the term that contains theta by itself. You have got it, but it is squared. So what you're going to do is you can square root both of them to get tan theta by itself. So tan theta equals positive and negative 1. Now you will look at the unit circle. You look at the unit circle and ask yourself, when is tan theta equal to positive and negative 1? I know tan theta of pi by 4 is positive 1. But if it says positive 1 and negative 1, we will look at all the 4 quadrants. Because remember, 2 quadrants have positive values, 2 quadrants have negative values. So if it's positive and negative, all the reference angles of pi by 4 will satisfy the condition. So my solution is theta equals to pi by 4, 3 pi by 4, 5 pi by 4, and 7 pi by 4. These are my 4 solutions for question number 2. Okay. Now let's look at question number 3. Question number 3 says, so I'm just copied from the notes packet, page 16. Sine square theta equals 2 cosine theta plus 2. So this is what I said, that you have both sine and cosine in the same equation, not possible for us to solve it. So you try to convert one to the other. The minute you see a square, you should be thinking of Pythagorean ID. Go ahead and look at your Pythagorean ID statements, the difference form of it, and sine square can be replaced with 1 minus cosine square theta equals, the rest of it you want to keep the same. What do you notice in this statement? In this statement you notice that there's only cosine square. And you notice that it is still, but it is a quadratic because the cosine is squared. So let's write this quadratic equation in the standard form. Whenever you see a quadratic equation, unless you're taking square root on both sides, which is a square root method, you always want to rewrite it in the standard form. Standard form means everything on one side, 0 on the other side. Except cosine square theta is going to be the leading term, it's going to be the first term, and the square term you want to normally keep it as positive. So let's move both of these to this side. So when I move this to this side, I have cosine square theta becomes positive 2 cosine theta stays as the same term. This 2, this, and this has been moved and becomes positive. And 1 is positive, moves to the other side, becomes, that's what happens here. So I'm going to rewrite this. So cosine square theta plus 2 cosine theta plus 2 minus 1 plus 1 equals to 0. There, I have got my standard form. That's always your goal. Your goal is to write it in the standard form. Now, can we all try to factor this? What do you notice? It is we talked about factoring in the previous class, that you have to look to see what pattern it is and what kind of factoring you do. I noticed that this is a trinomial. Therefore, factors of 1 that add up to 2. At any given point of time, if you want to practice on your own, please just hit pause for my video and do the work, and then come back and check if what I've written is correct. So factors of 1 that add up to 2 are 1 and 1. 1 times 1 is 1, 1 plus 1 is 2. That means my two factors are cosine theta plus 1, cosine theta plus 1 equals to 0. But from both of these, I get only one solution, which is cosine theta equals to negative 1. When is cosine theta equals to negative 1? It looks like it's a quadrantal, because 0 and 1 for cosine and sine is quadrantal. So how does it go? 1, 0, negative 1. So it looks like it's at pi. Therefore, theta equals to pi. That's my solution. So anybody who hit pause and did their own work, if you can check, and if you got theta equals to pi, you are on the right track. And I'm going to remove this piece of paper, and then we are going to look at 4. So 4 is cotangent square theta minus cosecant theta equals to negative 1. This is what I start with. Again, combination of cotangent square and cotangent and cosecant. I want to make them the same. So what I do is I replace cotangent square, because cotangent and cosecant are linked through Pythagorean ID. Cotangent square, go ahead and look at your Pythagorean ID. Cotangent square can be replaced by cosecant square theta minus 1. This thing can be replaced, and then the rest of it stays the same. And I'm going to bring the negative 1 to this side, because anyway, I'm going to write it in the standard form. So this will have plus 1 equals to 0. And then let's go ahead and open up the parentheses, and let's see what I have. Cosecant square theta. And then the next term is minus cosecant theta. And this is negative 1, positive 1 cancels, and therefore I'm just left with a 0. So what do you notice here? What do you notice here? Please try to factor without looking at my work. So you can hit pause and see if you can factor this. Everybody should be able to factor this. There are two terms. It's not difference of square, because this is not a perfect square. But what you notice is both these terms contain at least one cosecant theta. So I can take out the cosecant theta as the greatest common factor. So cosecant theta, what's remaining here is 1 cosecant theta, because it's squared and you pull out 1, and you've already pulled out 1, so only 1 will remain. And remember, you're factoring, your goal is to solve. That means you'll set each of them to be 0. Cosecant theta equals to 0, and from the second one, cosecant theta equals to 1. And remember, when we work with cosecant, we write it as a sine theta and write the reciprocal of the ratio. So this one you'll write as sine theta is equal to, reciprocal of 0 is undefined, this is undefined, sine theta is never undefined. So I don't get a solution from this side. But let's see this side. Cosecant theta equals to 1, that means sine theta is also equal to, reciprocal of 1 is 1. Therefore, theta is equal to, when is sine theta equal to 1? Sine theta is equal to 1 at pi by 2. Please look at the unit circle. It's a quadrantal angle, and you will find it is 1 at pi by 2. Alright, so hopefully we are all getting the hang of how to use different IDs to solve for a trig equation. A lot of times it gets converted to quadratic equation, and then you factor it. But you have to start with using Pythagorean ID. So let's do number 5. In number 5, let me write it down. 2 tan square theta minus 3 secant theta plus 3 equals to 0. You have enough information. Here we go, sorry. You have enough information that you can hit pause and try to solve this by yourself. This trig equation has a combination of tan square and secant. tan square is connected to secant with a Pythagorean ID. Please look at your Pythagorean ID and see if you can replace this tan square with some form of secant theta. Yeah, can we all try to do that and see what happens? So basically, don't forget the 2 outside. The 2 outside remains as 2. It's tan square theta that gets replaced by secant square theta minus 1. If you look at your trig ID, the rest of it remains the same. Then my goal is to write this in the standard form. For me to write it in the standard form, I have to open the parentheses. So 2 secant square theta minus 2 minus 3 secant theta plus 3 equals to 0. I can combine the 2 constants. So my my standard form will be 2 secant square theta minus 3 secant theta, and then plus 3 minus 2, that's going to be plus 1. Negative 2 plus 3 gives you plus 1. Now let's go ahead and factor this. So this is a factoring that I feel is a little more complex. It's a little more complex. So let's go ahead and see how we can do this. It is a trinomial. It is a trinomial, but it is a trinomial with the leading coefficient is 2. So remember, I can't just say what are the factors of 1 that add up to negative 3. This doesn't work when you have a leading coefficient that is not 1. So basically, at this point, because this is a little more complex, I tell my students that it's okay that for us to factor, let's replace secant theta with x. And then we have to replace it back when we finish the work. So let's go ahead and do that. So this becomes 2x squared minus 3x plus 1 equals to 0. When I see it in this form, it's a little easier to factor, correct? So what do you do here? So this is the one where the leading coefficient is not 1, it's 2. So you multiply this. Factors of 2 that add up to negative 3. Negative 2, negative 1 I think works. Yes? So I write it as 2x squared minus 2x minus x, right? Minus 3x is replaced as with these two. It's the same thing. You're not changing any value. Now you have 4 terms. You will do grouping. Remember, please remember your factoring. You can't forget these things. So between 2x squared and 2x, I pull out 2x. What's remaining? X minus 1. Here I want to pull out negative 1 because you want the x to be positive inside. So x is positive, and from positive 1 you pulled out negative 1. So negative 1 is remaining. So I'm running out of space. I'm going to go ahead and continue on a different piece of paper. So my 2 factors are the coefficient becomes one of the factors, 2x minus 1, and the common binomial becomes the other. That means from here I get x equals to half, and from here I get x equals to 1, right? X equals to half and x equals to 1. So if x equals to half and x equals to 1, that means now at this point you want to substitute it back, because remember, you are not solving for x, you are solving for theta, and initially you had replaced secant theta with an x, so now it's time to replace it back. Secant theta equals to half and secant theta equals to 1. Alright, everybody okay so far? Alright. And then, now I want to look at the unit circle, but instead of secant theta, I want the reciprocal, which is cosine theta. I use reciprocal ID equals to 2, and that's not possible at all. Cosine theta can never be equal to 2, because remember that the range of cosine is positive 1 to negative 1, or negative 1 to positive 1. But this will remain as 1, because reciprocal of 1 is 1. So when is cosine theta equal to 1? Cosine theta is equal to 1 at theta equals to 0. That's your solution. That's it. So that is number 5. That is number 5. We'll do one more, which is number 6. Yeah, everybody okay so far? All right. You can hit, like I said, you can hit pause anytime, replay it, and then look at it again if something was not clear. I'll keep going. Number 6. I'm going to look at number 6. Okay, let me write this down. Sine 2 theta equals 2 sine theta. Slightly different. You're seeing double angle here. You're seeing double angle here. when you see a double angle, yeah, they cannot be treated the same. 2 sine theta, sine 2, because this has got, the theta is multiplied by 2. Here just theta. But what you can use, we all know about double angle identity. So sine 2 theta using double angle identity can be replaced by 2 sine theta cosine theta. And this stays as 2 sine theta. Let's bring everything to one side. Please don't try to divide by 2 sine theta because you shouldn't be dividing functions. You can move it around. So 2 sine theta cosine theta minus 2 sine theta equals to 0. Bring everything to one side. And what do you notice here? I can factor because 2 sine theta is in both the terms. That means I can take that out as the greatest common factor. So 2 sine theta, you pull out, what's remaining is cosine theta minus, everything is pulled out, so just one is remaining. How do you know you're correct? You can always multiply it back. 2 sine theta cosine theta, correct? 2 sine theta times negative 1 is negative 2 sine theta. And then you want to solve by setting each one of them to be 0. 2 sine theta equals to 0. And cosine theta minus 1 equals to 0. From here you get sine theta equals to 0. When is sine theta equal to 0? Sine theta is equal to 0 at 0 and pi. Okay, now let's look at this. Cosine theta equals to 1. When is cosine theta equal to 1? Cosine theta is equal to 1 at 0. But we've already got 0, so you don't have to write it again. It's extraneous. So my solution is theta equals to 0 and pi. Okay, so that's your solution. Alright, so hopefully we've got the hang of it. There is also 7 and 8. Please take a look at, especially 7. 8 gets a little more complicated, but I want all of you to take a look at 7, see if you can solve it without me showing it. And please look at the key. Key is always posted in Schoology. Look at the key in Schoology and see if you get the solution that I have put up. And we will stop now.